small amount of time. But then again, if you want your model to be more precise, you might need to include the oral cavity. So the nose, the oral cavity, a couple of months back. I'll pass this around, but one thing to appreciate here is these are the two sides of the nose. See how thin the cross sections are. So imagine you getting a cold and the mucus plugs. So it is quite easy to fill that blockage in your nose. And then it goes with the rest of the tract. So I'll pass this around. Okay, so that's the nutshell definition of the URT. Now let's come to the LRT. The lower respiratory tract, or the LRT, includes the lower part of the trachea uh, and the lungs. I'm going to get into the details of the lungs in a while. Now, if you just think about the functional regions of the lung, like what each part of the lungs do, they have three different parts. One is the conducting stage, where the air from the trachea is brought into the lungs. Then the flow gradually transits to the finer channels, and eventually you have the region where there is gaseous exchange with the pulmonary veins and arteries alveoli. So it has three different morphological zones. So the lung is divided into the conducting, the transition, and the respiratory zones. Now, in our models, the work that we are doing right now, I would say we are still in the conducting phase. So the models that we are building, they include till generation 3 or 4. As we go finer, modeling can become tricky in certain sense, but it may also become simpler in certain sense. As we will see probably by end of today, no, actually tomorrow, that by the time we reach the respiratory zone, the flow becomes laminar, steady. It doesn't have any time variable component. So simulation wise, it becomes easier as long as we know the geometry. While if you think about the upper respiratory tract, even for that matter in the conducting region of the lungs, the dVdt component, the unsteady component could be strong, and there could be some turbulent features. So we have to model the flow accordingly in those regions. Okay, so these are the nutshell definitions of the URT and the LRT. Let's now go into the details of each of them. So first, the upper respiratory tract. Or the upper airway. Or airspace. So, as I said, those include the nasal cavity, the oral cavity. Let me write out the details of each. So this region also goes by the name extrathoracic region of the respiratory tract. I don't think I've ever used this term in any of my papers, but if you read papers with authors coming from clinical backgrounds, you might come across this alternate names for the URT. So first, let's write about the oral cavity. So this is the mouth, sometimes also known as the buccal cavity. So, as a fluid mechanician, let me go a little further back by a few years. The way I started working in this space is uh, during my second postdoc when I was at a medical school, and the position was with the ENT department, ear, nose, throat. But the group that I was working with, they were mostly working with the rhinologists. Rhinology is the science of the nasal pathway, drug delivery. They have to do some kind of surgical correction, those things. So we worked directly with the clinicians. The project was getting funded for drug delivery to the sinus cavities. All fine. So we just dealt with the nose. But where does this oral cavity come in? So we hosted a summer student from Brazil. She was actually a dentist, and initially as an engineer, as someone coming from my undergraduate was in civil engineering, then I did engineering mechanics for my PhD, did theoretical fluid mechanics, did some experiments in Japan. It was quite odd to me that I'm working in the same lab with a dentist. And then I realized that they can develop these digital models of the oral airspace. And it is important if they do any kind of surgical correction to the oral airspace, and that's done by the dentists. It is important that the airflow is such that there is enough heat transfer or optimal heat transfer with the air and the surrounding tissues. Otherwise, the patient won't find himself or herself comfortable enough. So they are still interested in this kind of CFD simulation of air moving through the oral cavity. So she would develop his geometries before surgery, after the surgery. I think the problem that she was working with was the cleft lip syndrome. So there were models that there were CT scans she collected at her hospital in Brazil, and she developed those reconstructions in our lab and then ran the simulations. So based on if you guys eventually do any biomedical research or if you're interested in this space, you never know what kind of clinical connection you might see, which would meet your aesthetic of the mechanics. So the oral cavity. The next one is the nasal cavity, which is, if you look at the literature, most people are working in this space because, as I said, 90% of the time we breathe through the nose, so it is important for infection transmission. And because most of the initial infective sites in our airway can be accessed through the nose, we are interested in developing breathing models and drug delivery models through the nasal cavity. Also, there are some new applications that are coming up. So, for example, one of the trickiest things right now for drug delivery is to send drugs to the brain. So, we have seen that if you access it through the nose, in our olfactory loop, which is the upper wall of the anterior nasal cavity, it is easier to penetrate through that region and cross the blood-brain barrier and reach directly into the brain. It is an upcoming area of research, but so the nasal cavity could be relevant in many different ways. And if we can really control the delivery of drugs through the olfactory route into the brain, this would be a big thing in this field. So nasal cavity, based on the modeling standards, it may just include the central airspace. And by central airspace, I just mean the central region going through the nose without the additional appendages. Now you can see the appendages in this 3D print. So this sac-like structure that is jutting out, or this region under the forehead, those are all sinus cavities. Now there are four different kinds of cavities, and we are going to look at them in a moment. But these cavities, they don't take in much air flux. So most of the air that we are breathing in, it just moves through the median central part of the airspace, goes into the trachea and into the lungs. Not much goes into the sinus cavities that are adjoining to that central airspace. So for the sake of quicker simulation, most of the times we might uh, take those sinus cavities out of the model and then model the airflow. But what if you actually want to send drugs to the sinus cavities, which is what I was doing 8, 9 years back as a postdoc. The target site was sinus cavity because the disease that we were trying to treat was the sinus inflammation. So then you do have to include these cavities. So based on the modeling standards, it may just include the central airspace or the central airspace plus the sinus appendages. And if we do include the sinus appendages, then that model will be called a sinonasal cavity. So in the letter, we call it the sinonasal cavity. And you can probably sense that once we include those adjoining structures, the airspace becomes morphologically even more intricate and complex. So from the nasal cavity and the oral cavity, now we come to the pharynx. So the pharynx is what we in common terms we call as the throat. And as I said, it has two parts, nasopharynx and the oropharynx. The nasopharynx is critical in the sense that most or many viral infections, their initial trigger sites are at the nasopharynx. There are two reasons for that. So the nasal lining, starting from the anterior airway to the pharynx, they contain some cell surface receptors, which is what the virus will bind to intrude into the cells. Let's not go into the details, we're going to cover the details later on, but it's the type of the cell surface uh, receptors that dictates which virus would enter the tissues. Now, in the outer part of the nose, we do have a thick layer of mucus. Even when we are fine and healthy, there is a thicker layer of mucus, which gradually slims down as it goes further downward. And by the time we reach the nasopharynx, it is easier for the pathogens to actually intrude into the tissues, navigating through that mucus layer. So the first infection trigger site is the nasopharynx. For viruses like for example, like for common cold, when you get a throat infection, that is actually coming from the nasopharynx. When I started modeling for SARS-CoV-2, I was trying to read the biological literature, and they did some experiments back in the summer of 2020, and they realized that the infection is primarily starting out initially from the nasopharynx, and then it goes to the lungs, of course. But the initial trigger site, the initial hotspot of infection, is at the nasopharynx. The nasopharynx is important like that, that's the upper part of the pharynx. As we go lower, we come across the oropharynx. Now, the oropharynx, along with this kind of viral infections, right now in my group, we're also working on pox family viruses. So for pox family, we know that the smallpox has been declared eradicated by WHO in 1980. But since we have a lot of biological literature on smallpox, we're actually trying to model the infection transmission process for smallpox. And that actually starts from the oropharynx and then goes further downwind. If our work holds ground for smallpox, hopefully we'll be able to extend it to monkeypox because that is the emerging pathogen. So basically, we are using this as validation, the smallpox data, and then going to the monkeypox. Similarly, if you think about many other viruses, along with other routes for transmission, inhaled transmission could be critical. And the first thing that we need to figure out is what is that infection, the initial infection hotspot in the area. and then you can use your modeling knowledge, fluid mechanics modeling knowledge, to figure out which particles, what kind of particles would be ending up at that particular site. Anyway, so pharynx, which is the throat region, between the larynx and either the mouth or nose, is classified into oropharynx. So this is between larynx and mouth. That is one way to think about it, because the main airspace, the region where the mouth space connects, we take that region as our pharynx, or it is the lower part of the pharynx. And the upper part is the nasopharynx, which is the region between the nose and the oropharynx. So this is the upper part of the pharynx. So that's the pharynx. So after this, we move further downwind and then we come across the larynx. So the larynx, as I said, the main important part over here is the presence of vocal folds. Now, the other line of research that is going on right now. So in my group, I mostly look at inhaled transmission. So we are breathing these particulates inside our system. But folks who are looking at what is expelled out, they are also really interested about this particular region, because as we talk from our vocal folds, they move, right? And the particulate size distribution that we are ejecting out as we speak can be traced back to what kind of fluid separation is happening near the vocal folds. So if you look at some relatively recent papers over the last 2 3 years from Howard Stone's group at Princeton, he has done some work on the fluid mechanics near the vocal folds. So this is important for modeling particulate spread in the room as well, because those particulates are coming from that primarily. They're also coming from the upper airways, because as the air brushes past the mucus, there is also some fluid fracture going on, and then some particulates are being generated from the upper respiratory tract too, and even from the oral cavity. And finally, and Howard has done some work on that as well, as we move our lips, as the lips separate, there is again some film formation, which leads to tiny aerosols expelled out into the air. But anyway, so larynx, which is the constriction to the trachea and contains the vocal folds. So this constriction part is also significant in the sense that, and we will see this I think tomorrow, the airspace, if you think about the main airspace, the cross-sectional size stays very consistent until it hits the larynx. And then there is a very sharp narrowing in the cross-section. And then it again diverges out at the trachea. So because of that converging track and then a diverging geometry, we see very strong vortex formations just downstream from the larynx. And those vortices are strong enough to impact local particle transport. And that is another main thing that we are working on in terms of what are the dominant structures from the flow field in the respiratory tract that can impact particle transmission, be it for drug delivery, be it for infection transmission. So this is the constricted region just before the trachea, so to the trachea, and contains the vocal cords or vocal folds. So during swallowing, as I mentioned initially today, so during swallowing, a trap door, it's like a flap called the epiglottis, opens up and covers the opening into the larynx. To avoid food or water from entering the lower airway. So this is what it should be happening ideally, but still we do choke, right? We do choke on our food, we do choke on liquids, and even if we don't choke, there is a mechanism called aspiration. So there could still be some liquid components that might be finding their way into the lower airway, which could be relevant, especially for infection transmission. For example, as we know that the initial infection spots are in the URT, the upper respiratory tract. So think about a situation where there are some infected regions in the upper respiratory tract. Now, these are all covered with liquids. As we breathe in, there is some viscoelastic stretching of those liquid layers, those mucus layers, and they might separate as the liquid separates from the cavity walls. Now, where is that liquid going? They might be getting swallowed, fine, but if they're not, they might be getting aspirated into the lower airway, and they can carry a high concentration of pathogens from those infected upper airway sites directly into the lungs, which can lead to secondary infection. So that is one possible mechanism. Also, when someone is sleeping, we aspirate more, and that is another route through which liquids from the upper tract can enter the lungs. If those liquids are infected, that leads to a mode for secondary transmission or secondary launching of infection in the lungs. Okay, so let's now share this visual with you guys. So this is included in the printed pages that I shared with you. So this is the upper respiratory tract, basically. So if I take a vertical cross section through this model, this is what it would look like. The nasopharynx, as you can see, is over there. This is the mouth space, so it connects with the main air space here. So whatever is above that is considered typically the nasopharynx. I don't think I have marked the oropharynx here soon, but the oropharynx is this region, and then this is the larynx, and then after this constriction, we go into the trachea. The simulation that I'm planning to run with you guys in this class would include a geometry that is still over here, till the base of the nasopharynx. And that geometry that I built was meant for drug delivery in the sinus cavities or somewhere in that region. So I did not include the rest of the geometry, but we have other works, and you are going to see some examples as well where we go further down way into the lungs. But since the geometry that you are going to simulate ends over here, you won't come across this strong vortex region that emerges here because of this narrowing. There is roll up of fluid layers, and we get some very strong vortices over here. Okay. Let me write a few comments over here. So these are the URT regions. So in this course, we are going to model the inhaled airflow and particle transport focusing on the mechanics in the upper respiratory tract. The geometry that you are going to see would have its lower extent as over here. So the outlet for the flux, so the inlet would be at the nostrils. So this would be the inlet. The air goes all through and it escapes the geometry that I've built for you guys through this outlet. Now the oropharynx is this region. Basically, this part is the oropharynx, and let's call the pressure at the inlet be P in and the pressure at the outlet be P out. So in the simulations that we are going to run, we are going to assume that P in is 0 pascals and the flow being driven by the pressure gradient. We are going to assume some negative value for the pressure at the P outlet. And I think we are going to target a particular living weight. So the simulation, the scheme is going to iterate over that delta P to eventually achieve that particular flow rate through the muscle cavity. So the flow would happen, the flow would be pressure gradient driven. So in this graphic, P in would be greater than P out, and typically we enforce P in as 0 pascals and P out some negative value. We are not looking at simulating the flow field outside of the nose, so it doesn't really matter what we take as P in. It's just a data base pressure. But if you are actually trying to model a person sitting in a car or inside a car or in a room, you might have to think about what the precise value of the P in might be, because then your data pressure is somewhere else. Okay, so the P in is obvious, it is the pressure at the nostril plane. Now the P out, I call it the pressure at the nasopharyngeal outlet. So the geometry that I think is shared with you guys, the anatomical part ends over here at the base of the nasopharynx, but after that I have included a straight tube that goes vertically down just to make sure that the flow is well developed at the nasopharynx and we don't really come across any kind of end layer effects over here. So that straight tube that you will see is not anatomical, it is just to make sure that the field is well developed at the nasopharyngeal airspace. But if you are doing something further downwind, of course, you need to include all the other details of the anatomy. Okay, so this was just a cartoon. Let me now show you some pictures from the actual CT-based geometries that we have built. And the model that you guys are going to work with, I think it's the second one. But before that, this is a geometry that includes the nose part is from that same person, but the outer nose, as you realize, is not important for this model. We just need the internal airspace. But all this green, that green region over there, the red region, and for that matter, this top yellow part over here, these are the sinus cavities, and also this yellow region are the sinus cavities. So let me mark them out here. So this is a sinonasal geometry, which includes all the sinus cavities. So this is the frontal sinus. So until now, I think I've looked at over 200 sinonasal reconstructions from subjects. The sinus cavity does not look the same across any two individuals. It's all different. So some people have sinus cavities that are very tiny. Some have sinus cavities that almost look like the big horns of a deer. Now, some people, as we know in our family, some are prone towards getting headaches, some are not. So if the sinus airspace is tiny, that means it is easier to get occluded with mucus over there, right? And once that happens, that's when the person gets a headache. So the kind of physiological reaction we get once we get a cold or get a fever, that is very much dependent on the details of this of our anatomy. Thankfully, from our CT scans, my sinus cavity is wide enough, so I don't get headache that much. But my wife does. So I did not collect CT scans for her airspace, but I presume that it is smaller than mine. So this is the frontal sinus, and another interesting thing, some people. So these are our nasal cavity has two sides, right? They go into this sinus cavity. So these are that's why I said these are like horns. So some people might have a smaller frontal sinus on one side and a bigger one on the other side. So that happens as well. So it's nothing is symmetric as such. So for example, in this individual, let me see. So if you check this model again, you will see that the right side has a bigger frontal sinus than the left side of this person. In fact, let me see if I can use the laser pointer. That's why I asked you to bring the laser pointer. You have to come closer to. Anyways, so that's the frontal sinus. Now, this region over here, this yellow sacs, they are the ethmoids or the ethmoid sinus. So there's a little collection of a number of little small sac-like structures, and together that entire region is called the ethmoid sinus region. Then this single bulb-like structure. So this is where the two sides of the nose they have merged together, and then there is this cavity at the back. So that is called the sphenoid sinus. And this structure over here is called the maxillary sinus. So again, if you look at this geometry, these are the two big sacs that are on two sides. So these are the biggest sinus cavities, the maxillary sinuses. There's one on each side. Again, nothing is symmetric. Uh, the volumes of the maxillary sinuses on the two sides could be different for any individual. And when someone gets a cold, there is mucus inside. When we collect CT scans, we can see that the sinus has almost disappeared in the sense that there is mucus inside the cavity and there is hardly anything from there to move through. Another funny thing once happened. So anyone here does nasal irrigation, saline irrigation when you get a cold, like taking salt water and run it through your nose? So that's a valid treatment technique where you take in salt water through the nose, you drain it out to the other side. So it helps to disinfect clear out some of the mucus. So once while I was doing postdoc, we collected CT scans from this person, and then when we got the scans back, we saw that the bottom layer of the sinus is a plain, straight, thin surface, not anatomically curved like this. It's just a single plane, smooth single plane. Uh, which for you guys, why do you think that happened? Maybe there was some water remaining from the yeah. So the water was residing over there. CT scans, when we got the images back, they are less of the radio density, right? So the radio density here is different to the Latin diastase. So we saw that there is something over there which has a very flat surface. And initially we did not know that the patient was doing this irrigation. It was not recommended to him. And the doctors were confused as well. Usually we did realize that is the water is having over there. So those kinds of funny things can happen as well when you collect these medical scans and you try to build the geometry. Okay, so but as I mentioned before, that most of the times, especially for infection transmission studies, we don't include the sinus cavities because the target sites of those pathogens, they are not in the sinuses, and we can remove the sinus cavities and just focus on the central air space. So very little air enters the sinus cavities. Which, by the way, let me mention one more thing over here. Because anyways, for any healthy subject, very little air would enter these cavities. And the biggest cavity over here are these maxillary sinuses. For some people, that entry of air into the sinus cavities is even less than any other healthy subject. And as a result, they might need some kind of surgical correction. So the surgeon would actually open up the entry into this maxillary sinus to make sure that more air goes in. Because otherwise that patient is getting infection just from lack of aeration between the sinus cavities. So that happens as well, and we can get those information through this kind of digital models. So very little air enters the sinus cavity. So unless we are deriving vertical transport or flow parameters at the sinuses, we typically delete these sinus appendages while developing the respiratory physics model. Another critical thing over here is when you get the CT scans, I think all of us here have some kind of physics, engineering, chemical engineering, mechanical engineering background. We don't have the knowledge of the anatomy to do the segmentation from those scans and build geometries that are anatomically accurate enough. So if at some point you do work on spaces like this, maybe not even the respiratory geometry, some other organ in the human body, it is important to get feedback from the clinicians. Make sure that the anatomy is correct. And that segmentation process is painstaking. So typically when we look at the CT scans that we have collected, they get images at different penetrative depths through the entire head. So based on the size of the head, you can uh, use around 200 to 300 such slices. And then we have to digitally figure out where the airway is in each of those image scans and then build the model. And as a result, when we are looking at a particular scan, we need to know what is the airspace, where are the bones, where are the tissues, and that needs some medical knowledge. And that should be done in collaboration with the doctors. Okay, now for the simulation that we are going to run this week, hopefully, we are going to use this particular geometry. And as you can see, this does not include the sinus cavities. This is just the main central aspects. And we, along with running the simulation, which is going to include all these morphological details, we are also going to develop a theoretical model to study transport parameters on this geometry tomorrow. But in the theoretical model, we of course cannot possibly include all these different details in the anatomy. So there we are going to use a single cylinder system that goes with a similar curvature and essentially track a flux that goes like this. And we'll see what happens if we do that and what kind of differences we might expect to a full-scale 3D CFD simulation. So this, for the theoretical model, which we are going to do tomorrow, for the theoretical model, the highlighted region serves as the model inspiration. And this is, as I said, is the nasal geometry after the sinus cavities are removed. Now, someone asked yesterday whether these structures, these walls, they're moving, they can move. Now the question is, do we need to include that in our mechanics guided modeling? The answer is not obvious. It depends on the time scale of that motion. So when you think about particle transport, that transport happens over a very short time scale. And most of these movements, they happen as we inhale in and then we go into the expiratory phase and we expel the air out. So the time scale of that motion is much, much longer than the time scale of that particle transport. So most of the times, we assume that the system is rigid. Another argument towards assuming that is, these walls are mostly built of structures that are rigid, cartilaginous, bony structures. And the mucus, one may argue that it's a soft solid, you can assume it as a soft solid. What about it? Now, the mucus, the way it moves, the time scale of that motion is also much slower. So, typically in a day, we swallow. Anyone wants to guess how much mucus goes through our respiratory pathway in one single day when we are healthy? Around 2 liters. So we move 2 liters of, we generate 2 liters of mucus and then they move through our respiratory system. But that happens over 24 hours. So think about an aerosol or a droplet impacting on that mucus layer. So that time scale is much, much smaller than the time scale of motion of that residing mucus. So typically we take static rigid walls in our models, and that's what we are going to do this week as well. So the airspace is enclosed by rigid cartilaginous and bony structures. As a model idealization, we will consider a rigid geometry while running the analysis and simulations. Okay, but then again, if you are actually looking at a problem where you want to capture that time dependent effect of movement of structures, maybe not in this region, if you are going further downstream, you might want to capture the motion of the local rods, then of course it's can. Yes.
Fine. Taking the CT scan, what is the state of the person? Is he asked to
The cities, the image extraction takes place over a snapshot of a second. So it's just a snapshot in time.
all the slices in a snapshot?
So we don't see any kind of movement or blurry effect while doing these things. Okay, so anyone here has seen any human cadavers? Dead human tissues? No one? Okay, so I have a gruesome picture in that case for you guys. So this is cut to a real head. It's slightly old, the head, as you can see. But one thing that struck me when I first saw this is the picture that I took quickly, is how tiny the cross sections are. And we don't appreciate that when we are looking at these digital models and we zoom out, zoom in, and look at them in our computer screen. We don't realize how thin these cross sections are and how tricky the flow physics could be in this kind of region. So over here, this is the upper air space with this being the mouth. You can still see some tooth over here, and then it merges together. The epiglottis is coming up over here, and then it has degraded a little bit, but it's still there. Now let me share a funny story over here. So when I was a postdoc at UNC Chapel, we once designed a project which would need. So we were trying to develop CFD models of airflow through cadaveric heads. Uh, Cadaveric heads are easier to deal with because unlike someone who is living, you can move the head around, right, in different orientations. So we decided to collect cadaveric heads. I think it was in December. We wrote the proposal that we need 40 cadaveric heads. And the start date of the project was in June. And then it was submitted and eventually it got funded. So the first gruesome detail is when I was writing the proposal with 40 heads, and that project started in June, those heads were still living on someone's body. So that was the first gruesome thing. So we were talking about getting cadaveric heads in December for project that starts next year. The next funny thing that happened, so the heads, some of those heads were collected at Duke Hospital, some were collected at University Hospital. So Duke, everyone might know, it's like around 40-minute drive, 45 minutes drive along the interstate from University Hospital. So me and another medical resident who is very
School at donuts or like some sort of bond to sign?
yeah, some organ donors. Yeah. Yeah. So we drove our car on the interstate to get those heads. And on the way back, in our front, there were 40 dead heads. And the resident was driving and he was speeding. And we got stopped. The question is, I am just an engineer. He's a doctor, but not a full-fledged doctor yet. And we had like 20 dead heads in our trunk. The police did not open up our trunk, but who knows what could have happened if it did. So yeah, so this is a cadaveric specimen of the URT, and clinically it is called a sagittal cross section. By the way, is there any medical hospital nearby which where you guys collaborate with, can collaborate with?
One of the professors collaborates with PGI.
Okay.
This is a private hospital, so there is a private hospital called Max.
Yeah.
Some of the doctors study in PGI, so they kind of interact with each other.
Okay. So if you are really interested, maybe as PhD students, even in your spare time, go try see the cadaver lab, and just seeing them can give you new ideas of engineering physics research. Hopefully.
Two of the professors work in like related to bone mechanics. They have followers and certificate.
I actually like if you guys ever visit my lab, my office, not my lab, in my office I have a real human skull. So the American undergraduates, they find it funny that I have a skull in my office in a mechanical engineering building. Okay, so are we going till 11 or 10:30 now?
I mean, it is started clearly.
Okay, so I'm done with the upper respiratory tract. The next thing that we're going to move into is the lower airway and the lungs. So maybe we break for now and then come back to the lungs. So in the first session, we looked at the upper respiratory tract. Let's move further downwind to the lower airway. So this is the lower respiratory tract. Also called the lower airway or the lower air space. So this cartoon that you have here, this is the trachea. So this bifurcates from the primary bronchi. Nothing else is visible on this screen, but the primary bronchi is again bifurcated from the secondary bronchi, and then they bifurcated from the tertiary bronchi. That I think has been leveled here. And then eventually it goes to the bronchioles till the 23rd generation. Now, what you see on this one is a zoom out from the very distal end of the lower channels, where the gas exchange takes place. So these are the pulmonary, this red and blue are the pulmonary arteries and veins, and they extend the gas with the alveolar sacs. So let me write down some comments, part of which I already mentioned in the first session. So we have two lungs. They are shaped sort of conical. So the two cone-shaped lungs are located in the pleural cavities of the thorax. The thorax is a region anywhere under our neck till our abdomen. So the pleural cavity contains this set of lungs on either side of the heart. Functionally, that is important, right? Because the heart is the main engine in our body. It needs the oxygen, and the oxygen is coming from the airway. So it's goes over there. Now, I think a couple of weeks back, we were wondering about the structure of the human anatomy, and this is sort of heading into the open question direction. So we have lungs here. Heart is here. We are drawing air into our body. But this is not really the central part of our body, right? The central part is sort of here in your tummy. So the heart being the engine could have been at the center. Why is it not? What functional benefit do we derive by this structure, all this very critical structure going over here? Because if the heart is centrally placed, it is easier for heart to send blood pumping wise, reality is right. So the pumping efficiency would be better. It has to spend less energy to send blood to the rest of the body if it is centrally placed. Why is it so high up in our body?
because there are too many fine veins near the lungs. So if it is
Why are the lungs there? The lungs could have been here.
because of pressure.
The pressure drop. Can you explain more? What do you mean by pressure?
Usually pump
Pressure of what?
pressure of blood.
By that logic, why don't we have it at the center again? Then it can access the foot and the brain equidistant away. And most of us are short here, but think about someone who is over 6 feet. There the heart is so much high that has to pump blood so far away. I don't have an easy answer for you, so don't expect that I have an answer, but something to think about. Now, one rationale that I came up with is it's a combination of two mechanisms that's going on, right? The lower the lungs are, it will be more difficult to breathe because you have to impose the pressure drop, but this is not the blood pressure. This is the air pressure drop that we have to impose. Just like if you are drinking from a glass, if you're using a straw, it is easier to have a straw which is smaller and you are pulling the glass like this, rather than having a straw that is long and the glass is on the floor. Right? So having a short weight pipe makes sense because then you apply less pressure drop. But then comes the question of heart. So it's optimizing between the two. And really I don't have an easy answer. But this itself could be a very interesting bio-inspired mechanics problem. Like why is it like this? It is like this, we know that, but why is it like this? And if yes,
If it is water, the pump has to do more work to pump the blood on the upper part of the mouth.
but it has to do less work to send blood down there.
Maybe in the lower part it can go into some place
So
of
gravity, you mean?
yeah.
That's a good point.
And if it is located here, then to send the blood of upper part.
But then think about pigs. The pigs are not upright human beings. For them, also it is sort of like on the upper part of their physicality.
Same thing that maybe I didn't rephrase properly because there are too many veins inside this lung area.
Yeah.
So if it is closer to the lung is, whatever the reason for lung is, but if it is closer, then means there is less space to cover this.
So you were saying that it is driven by the location of the lung.
Yes, because the concentration of these veins is
Yeah, that is true.
very high.
The gas exchange has to happen with the lungs. So the vein concentration, the artery concentration is high over there, but your rationale is the heart should be as close to the lungs as possible. So it is near at least.
Independent of the fact why lung is there, I am just telling why it is close to lung.
The lungs. But still, it is a combination of two factors. Right? We can place a lung somewhere else, and then the heart should be there. I mean, what was stopping God from putting the lungs back over here?
It is easy to mix oxygen with blood. So why it is close to the lungs?
Yeah, that is true. That we understand. That it has to be close to the lungs because the oxygen exchange, the alveolar sac takes the carbon dioxide out from the recirculating blood. It puts the oxygen in. So it has to be close to the lungs. But why the lungs are there? One argument is, of course, the pressure drop. We have to apply more pressure drop if it is further down the body. Right? But then why do we have our nose over here and not over here? So these are interesting questions that we don't think about. We just say,
I think it is related to brain.
Related to brain in what way?
To transfer blood to the oxygen to the brain.
So you're saying that the respiratory system should be close to the brain?
So easily transport blood to decrease the heart disease.
So you're saying that if we think of this as the human body, the heart should be closer to the brain because brain is the main thing that's driving the rest of the
That is the higher or tall and higher risk of heart attack. Then
those are anecdotal. I don't think it could be proven that way.
so gas exchange, one main thing is need to have large surface area somewhere in the body.
Yeah.
For us, it is this place because the surface area is very high. For fishes, or one thing you need is a big opening where you can get a lot of air because density is low. For fish, it is gills. Yeah. For us, it is mouth. It is sort of optimizing one way that we are eating also from here, and there is this epiglottis also. So one opening is required. Actually, maybe there are too many factors. Too many factors. Maybe the gravity factor is also important.
Gravity is important, but if you think about four-legged animals, then the gravity is distributed outward. What I'm trying to imply here is, as I said, I don't have a clear answer, and all your answers are valid answers. But bio-inspired robotics is an upcoming field. And these are some questions that people have not explored yet. Like, why should the brain be why should the heart be where it is? Why should the lungs be where it is? How does it relate to the location of the brain? And why do we have our nose over here and not over here? Central part of the body. Right? Anyway, so let's move back to the human body as we know it. So the two cone-shaped lungs are located in the pleural cavities of the thorax on either side of the heart. The lungs have some clear anatomical zones that you can sort of think about. And the right lung is not symmetric to the left lung. So we have some level of asymmetry as well. So the lungs have clear anatomical divisions called lobes. And the right lung has three lobes. The superior, which is the clinical term for upper, middle, and the lower or the inferior. And then the left lung has this should be two lobes, not two lungs. So three lobes in the right lung and two lobes in the left lung, just superior and inferior. Okay, so as a result, because of the two lobes in the left lung, this is also slightly smaller than the right lung. Okay, so now what passes to the lungs, this air that is coming in through the windpipe from the trachea, and then it goes into all these channels. So let me write down the details of that. And some of it we have also covered yesterday when we were talking about the lung generation. So the trachea sometimes also called the windpipe, leads to the conducting airways. As I said, if you just think about the regions of the flux, the air flux passes through in the lungs, conducting, transiting, and then where the respiratory gas exchange takes place. So this leads into the conducting airways. So if I try to draw a very crude sketch, so this is the trachea. So it bifurcates. So this first bifurcation is called the primary bronchi, and then they in turn bifurcate to form the secondary bronchi, and then it follows in a fractal nature, so they bifurcate as well to form the tertiary bronchi. So this is basically the conducting region of the lungs, and if I am so the model that we are developing conducting right now includes still this tertiary bronchi. And what I'm assuming in my work, if you are trying to track what is moving to the deep lungs, by deep lungs I mean generations that are further below. At this point, without modeling, because we are moving from the upper respiratory tract, which has strong time varying component, it is unsteady in nature, and the flow is going to be unsteady over here. So we end up on here. And whatever is escaping through this so-called outlets, we assume that that is moving to the deep lungs. I don't know a nice way to combine both unsteady modeling and unsteady turbulent modeling and then the steady modeling, which is going to happen in the smaller bronchioles. So I end my model over here and then track what is moving in through these outlets towards the deep lungs. So the nature of the numerical scheme for these two regions of the airway should be ideally different, and I don't know of any work that has managed to merge the two together. Now, from here, let me write down the definitions first. So the tertiary bronchi into several generations of smaller bronchioles. And this, as I said, are the conducting airways, and then the transit into the respiratory gas exchange zone, where you have the bronchioles, the alveolar ducts, and the alveolar sacs. The respiratory bronchioles, the alveolar ducts, and the alveoli. Okay. Now, in terms of the current state of modeling work for lower airways where things become laminar steady, anyone here has seen any work recently? Any paper that you might have read here? So there's a group at IIT Madras, Dr. Shamuddin knows about them, Mahesh Manchakra, they are doing a lot of work for this region beyond. Basically, they do start their model from the lower part of the trachea, but essentially they're modeling everything as steady state laminar typically. And they develop this model which tries to mimic the total surface area of the channels, but it is called a trumpet model. So that's a very useful technique to get some idea about what the flux would be like. But to my knowledge, the details of the anatomy in any kind of modeling work, I have not seen any paper yet. But I would still encourage that you guys look through the papers like this. Now, over here, as you are pointing out the surface area of the gaseous section, that is very crucial. So, you want to guess how big the surface area is and maybe how many times the surface area could be compared to the outer surface area of our body? It is 71 times. So, whatever the outer surface area is, the surface area over which the gas exchange takes place with the pulmonary channels is 75 times of that outer surface area. So the thin walled sacs called the alveoli, 50 to 140 meters square. So, and the gaseous exchange takes place with the pulmonary channels. And this is, yeah, so Josu Snistman, I have shared that paper on our shared folder. So there they're looking at, they have developed this CAD models with enough dimensions of the lung, and that according to them can have some relevance for the gas exchange. But a truly biological model that we can operate using our mechanics platforms, analysis, simulations, whatever, is still sort of another area. So this is all that I wanted to write about the lower respiratory tract. I have a very simple example problem for you guys before we move to the next part. So this is, I think, the first figure from a paper that I recently wrote. It has not been published yet. You can find it on archive. So here we are trying to uh, develop an understanding of secondary infection in the lungs. See, the argument is this is the upper respiratory tract, right? The upper airway, that's where the infections primarily start out. Initially, the infection hotspot is over here at the nasopharynx. But after that initial infection onset, doctors have seen that the bronchial infection also emerges pretty soon. Now that initially people thought that that is happening through tissue level replication of the infected cells and as a result the viruses. But the time duration needed for that level of progression of the disease was not agreeing with what they saw in real subjects. And many of this work came from the COVID-19 times. They saw that after the emergence of initial symptoms in the upper respiratory tract, we are developing bronchial infection within 2 to 3 days. And that is not enough time for the infection to progress through tissue level replication to the lower airway. So it was an open question, and I have been discussing about this question with a number of groups, including the Anti group as well. But there was this line of studies that happened in the late 90s and the early 2000s. They saw that this mucus layer that we have, it is viscoelastic in nature. It does undergo some viscoelastic separation. So if you let air flux brush past that mucociliary layer, there could be air space. Now, we also know that if you think about the mucus layers, this is the region where the pathogen concentration initially after the emergence of infections is the highest. What if particulates generate from that region get lost into the lower and can explain the secondary bronchial infection? So that was the motivation of this study, and yes, from the work that we have done, it seems like that would be the case. That would be a viable route where particles generated from the upper respiratory tract and move downwind. And because they are moving from here downwind directly, even particulates that are as big as 15 or 20 microns can move directly into the lungs. Unlike 15, 20 micron particles from outside, they have to navigate this very complex anatomy, and they cannot, because of the inertial dominance in the mechanics, they cannot move all the way to the lower. They will fall out of the streamlines, they will deposit in the upper part of the nose. But these particles, they get a fairly straight path to follow, and then they move into the lungs. And those being big in the sense 15 20 microns, are the biggest particles that we are talking about here. They carry more pathogens, and that can explain the secondary infection. So that was the story in the paper. It is still getting reviewed. It has been 7 8 months now. It went through the first layer of review, so sometimes things take a while. But the problem that I have is, it's quite fun that I have for you guys, because in the paper I mentioned what the lung generation is in this model, and now I realize that whatever I have in the current draft is inaccurate. So I said that it is still generation 2. Do you agree? Is it till generation 2, this particular picture? As I said, it's already inaccurate, so it's not generation 2. So what is the generation number here? How many outlets are here? 1, 2, 3, 4, 5, 6, 7, 8. So 3 to the power of 3 is 28 in the range of yesterday. So it's the third generation. The funny thing is, before I submitted the paper, we have a respiratory care program in the nursing program in our university. Our respiratory care specialist went through the text in the paper. He said it's all fine. It's in relation to. So I can actually, I have acknowledged that, so I can blame her as well. So, anyways, I thought I should include this into the material because even I mistook this 6 months back. So, let's write down some comments here on that. Okay, so the above graphic is from, let me write myself in third person here because if this material is shared, at least someone would know to look up the papers. It's from Dr. Basu's recent paper. Find the bronchial generation number considered in the idealized geometry. So we have 1, 2, 3, 4, 5, 6, 7, 8. Therefore, generation n will have 2 to the power of n outlets owing to the fractal nature of tube bifurcation. Therefore, here the number of outlets is 8. So it is generation 3. So I have to remember to correct this on the manuscript by the time the paper comes back. Okay, so any questions until now? Yes.
I think maybe it can be written in two ways.
Yeah.
It's the end of the third generation, the last point, or the beginning of the fourth generation.
Yeah. Beginning of the fourth generation.
That will remove the uncertainty maybe in reporting sometimes. That we did till the end of the third generation. Because the top part can be the end of second generation.
Right. But typically, if you look at literature, they don't do it that way. Like the non-mechanics community is very well established. It is older than the upper respiratory tract community, and they just refer to the generation number and they're supposed to understand what they mean. So they don't really. What you are suggesting is helpful in the sense that you are spatially locating what the extents of the model are. Like this before the generation post level. It is useful. Perhaps in our engineering papers we should take that approach.
The result at the end it can be used to maybe study the lower part.
Yeah, that's what I'm doing. So that's what I'm doing. That whatever is coming out here is moving into the new plants.
So who are these like typical reviewers, doctors or engineers doing biophysics?
So this paper is getting reviewed after Fritz, like one of the Fritz channels that we know, like one of the top three. So they are probably going to review like us with some bio interests. And this paper does not include any doctors as a co-author. So typically, if you the clinical journals typically would expect some doctors on the co-author list, and also you should be studying something which is more directed towards a particular pathogen or a particular. This is more about a mechanistic study about what is going on. Okay, so let's go to this table. So this is from one of the textbooks that I mentioned yesterday. I think it is from the biofluid mechanics book by P. Nithya Rasu. So I thought that we should I should include this into the material because it's useful. Take a quick look at what's going on. Initially, I got confused with, so for example, in generation 16, the table says that the number of channels is 6 times 10 to the power of 4. And I got confused because it should be 2 to the power of 16, right? But if you do a quick check on your calculator, basically it is just the order. So I think 2 to the power of 16 is 6, 5, dot, dot, dot something, and this is 6, 0, 0, 0. So he's just mentioning the order. So nothing changes based on that fractal calculation. But what is interesting is here, which even I had some lack in understanding on what kind of particular sizes could be entering this channel. So let's go to the last generation, generation 23. So there the size is what? 0.05 microns. So sorry, 0.05 centimeters. So that is around 500 microns. That is wide enough to let all the big particulates that we are talking about in. So we cannot argue that a 20 micron particulate is too big to enter that domain. They can if they are allowed to. It's just that the 20 micron, 30 micron particulates that we are inhaling from outside, because of the inertial dominance in their mechanics, they deposit, they cannot navigate this band and they deposit in the anterior parts of the nose. But if you have a 20 micron particle generated here, they have a direct access to the lungs. And then they go into the lungs and they have to tolerate those bifurcations, true, but there is nothing stopping them from getting in there. So that size, the typical cross-sectional size was an eye-opener for me. So I had not modeled anything in that domain, in that kind of generation number, but if you guys do at some point, or even if I do, we need to be careful about that. That mechanistically we stay realistic on what would happen and not ignore things. Any questions? Okay.
Yes. Number is it fixed or there are some variations?
The 23? To my knowledge, it is an approximation. And it is not a recent work. It is coming from quite a few decades back. But if you look at a replication of a real one, it is so complicated. I don't think people are that accomplished yet to get a more exact. Think about how many numbers are there. 2 to the power 23. Do you guys have calculator with you? Try that. I'm curious. Can you even generate 2 to the power 23? I know my phone cannot unless I do 2 times 2 times 2 times 2.
Can you? 256 into 256 is already 2 to the 16.
Yeah.
8
Yeah, and now think about how tiny the ones are. Fit everything over there. And these are 0.05 centimeters, so it's still some width.
Because this fascination of this fractal ordering thing with Mandelbrot and all those people, they try to find a fractal in everything. So, like,
Yeah, and have you guys read about self-organized criticality? There also it's the fractal nature. So there was a generation in the 70s, 80s, they did everything with fractals. Okay, so I wanted to cover this anatomical details because that's where we are heading into. Now we are going to connect the mathematics that we had developed yesterday with a real human respiratory system. So before I move on, any final questions on this? Okay. So,
just
yes.
question. When you smoke,
Yeah.
how far up is like burnt smoke particles?
You need to ask when you smoke. I don't know.
I don't want to be personal. So, like, how far it reaches in this order of 2 to the power what scale?
I don't know and I don't want to know.
Actually, I did some sort of this work in my master, and my supervisor used to smoke. So he asked this question, and I found out.
Okay.
So what I understood means not an expert, but as I already told you, there was a size thing. That this much size will go here, this much size will go here, and the smallest size will reach to the end.
Yeah.
So, as per his request for me to investigate, I found out that it doesn't matter if it's smoke or anything else. It, it has to be of that much size. If there is construction happening and that size is there, it will go there, and the silicosis and all those things can happen. But the point is, if you continuously smoke and some part of this 100-meter square is getting damaged, it cannot recover. The first thing is that it will never recover. Only what you can do is you can try to increase the efficiency of the remaining area using enhanced this blood circulation.
Okay.
If you have smoking, it is already reduced, your efficiency is reduced, the area is gone. But you can increase the efficiency only by.
But is that proven? Like, if you read papers?
I read a lot of papers. I tried.
Are you trying to scare me?
No. No.
No, actually, like during COVID times itself, simultaneously the daily air pollution was going on.
Actually, even before COVID, so the group that I was part of at UNC, they were. So even when I was at UNC, there was a group doing tobacco smoke inhalation studies, especially because that was when 2016, 17, right? So the e-cigarette concept was coming up. Now they know that e-cigarette is also bad, but they were doing a lot of studies back then. And yes, so this kind of, as you said, like it doesn't matter what the particle is, there is size demarcation. One thing that we need to be careful while modeling smoking is you don't need to worry about the nasal cavity details, right? So the mouth gives a more direct access. So that means the 20 micron particles that might have been screened in the nasal cavity are probably going further downrange. So that is concerning in that sense. But the secondary thing that comes up, and I don't know how much we will explore that, is we have an inner replenishment going on. So the mucociliary fluids they recirculate, and that can clear out some of the pathogens, some of the contaminants. Now, whether that is sufficient for someone who has been smoking for the last 20 years, 30 years, that's a good question.
But I was on the end of.
Many smokers, since we are talking about smoking here, they also exhale through, they take in through the mouth, they exhale through the nose. That itself is a very interesting mechanics question. Because the flux going in through the mouth, and we try to not get things into the lungs, and we are exhaling through the nose. But still, it's an uncontrolled mechanism, right? There could still be some population going on down the way. And I'm pretty sure no one has looked at it yet, but something that could be very interesting. Any other questions? Okay, so now we are again going back to sort of where we left off yesterday. But unlike yesterday we were just looking at single aerosol motion through fluid. I did not bring in anything related to the nasal cavity deposition or anything like that. But now we have to think about how we can connect the mathematics to the physiological system that we are trying to study. So this is now aerosol deposition in the nasal cavity. So from yesterday, we are going to start using this equation that we had derived yesterday. So Stokes number dv bar prime dt prime is equal to v settling over the characteristic speed of the ambient flow times the non-dimensionalized g minus v bar prime relative. So just for the sake of completion of the lecture notes, let me write down these definitions. So v bar prime is v, which is the particle velocity, over the characteristic speed. V bar relative is v bar relative prime is v bar relative over u naught. or V bar minus V fluid, which is air over here, divided by U naught. So many times when we run these modeling studies and the papers that we come across, they ignore the gravity. They don't consider gravity while trying to model these studies, including the paper that we saw last night. Everyone here tried to read the paper last night? So their Sunny had ignored gravity as well. So what is the argument towards ignoring gravity? That was a question that came up when I first started working on this field as well. Well, for the bigger particles, gravity does play a role, right? Like if you have 100, 150 micron particles, gravity would play a role. But the paper that you guys read last night was it on drug delivery or something else? That was on deposition of what? Aerosols. What kind of aerosols? For pathogens, for infection transmission. So I think he first did a spatial modeling, like in space, and then he tried to look at the event transmission. So he is talking about aerosols that are tiny. Aerosols are droplets that are tiny in the sense that anything bigger than multi-50 microns would a sediment under gravity in space. We are not going to inhale those things. We are inhaling just those very small particles. And for them, gravity could be ignored. Even if you do turn on gravity, you will see that the regional deposition does not change much because that inertial nature is not there in experiments. So since we are trying to develop an analytical framework for this, it's not a numerical framework yet, let's ignore that. That's the argument. Because the particulates are small enough. So ignoring gravity, we are left with Stokes number dV bar prime dt prime is equal to minus V bar prime relative. Okay, let's now try to apply this. We are trying to get a physical derivation or physical understanding of what is going on in real scale. So let's now get rid of the non-dimensionalization and put it the terms over here. So Stokes number we derived yesterday is U naught rho p d square cc over 18 mu d. U naught is the characteristic speed, d is the characteristic dimension where we are studying the transport process, times d. V bar prime is V bar over U naught. dt prime is t over the characteristic time is derived from the d and the U naught that we have assumed. Right? And this is equal to minus V bar minus V fluid bar divided by U naught. So dV bar dt is equal to same as before, so minus V bar fluid by U naught. Let's now see what we can cancel. We can cancel the d's. We can cancel this U naught V. Okay, so let's box this up. And I'm going to call this as equation A. Let's get rid of the numbers from yesterday because things were already getting confusing. Now over here, what is this part? So if we check the dimension here, and personally I'm bad at remembering formulations, so I'll check the dimension, what this implies. So rho p is L to the power of minus 3, d square is L squared, slip correction factor is dimensionless, divided by mu is kg per meter per second. So kg this. So this becomes 1 over t, right? Or rather, sorry, so this becomes 1 over t inverse. So this is t. So this is what we have derived as the particle relaxation time rate, the tau. So this coefficient over here is a characteristic time. So from the formalism derived yesterday, this is tau, which is the particle relaxation time. Okay, so let's now write this formula hence as tau dv bar dt is equal to v fluid. Flow velocity, v is the particle velocity, dv dt is the time rate of change, so that's the So now we are going to use this. So what we are trying to get at is, what if we apply this formalism into a real respiratory tract, or at least an idealized geometry that is inspired from a respiratory tract. So let's look at what I mean by that kind of idealization. So let's now consider an idealized nasal cavity. So when I say an idealized nasal cavity, I'm getting inspired by something like this. So we can think of this as sort of like a circular arc which eventually straightens out. We are not going to think about the load array or boundary position line. We are just trying to develop a clean model for what is going on in the nasal cavity in the central space. So based on this, what I'm trying to draw here is something like this. And the cross section is consistent, and it could be the main cross section from a real anatomy. And that's why I asked you guys to bring your MATLAB today, because hopefully we can solve some numerical examples by imposing the real cross section of that. But this is what I mean, but let me add the details here. So this is the central axis. Now, I already did a very bad job of sketching this. This is a circle, and this is an outer circle with same curvature. Let's assume that the center is here. Oh. Now, the distance to the central axis of the airspace is L naught, let's assume, with the radius, the so-called radius being L. Okay. Now we are going to keep count of how far into the airway we are in using that S coordinate, or the value, let's not call it S coordinate because we are using a different coordinate system here, whatever the value of that S is. And we are going to track particles from here to where it goes. So there is the ambient air flux going through, but based on whether it is an inertially dominated particle trajectory, it can end up over here, right? There is nothing stopping. If the particle velocity is initially quite high, it just shoots and end up over there. Similarly, if the particle velocity is slightly lower, it can try to follow the streamline for a while, but it can end up over here. And that's where I'm trying to get at here. Because this equation that we have just derived, if I can use this equation, integrate it, and figure out where the location of the particle is going to be after a certain while as we integrate over time. If we see that it is landing on any of those wall regions, and if we can develop the mathematical condition for it, we will have a classical mechanics guided framework to predict whether the particle is going to end up equilibrium on the air walls or if they're going to go further downwind into the runs. Okay, so that's the motivation. Okay, so what else do we need here? So this is, we are going to use the the cylindrical polar coordinate system. So while it is a 3D model, but we are not assuming any kind of effect in the direction normal to the plane of the screen. We have this distance or the location as r. So wherever the particle might end up as it moves through this space, we can note it by r. Along with, we need another second coordinate, which is this theta. So knowing r and theta should be sufficient to know where the particle is. And what else do we need? I think that's it. Any question before we move any further? Do you think this is a self-sufficient setup to know about the particle dynamics as well as we can use that equation that we have had before?
Yes,
Huh?
yes.
Yeah, of course, we need the initial conditions with all the differential equations, but I'm talking about the geometry, realized geometry that we have. The total length that is relevant. At this point, we are assuming that this is a 270 degree. Right. So that itself will tell you what the total length is. And in fact, to develop the analytics or the analytical formula, we don't need the actual value of it. We're just assuming some symbols, right? But we are going to solve some real examples where we are going to use those specific numbers. So S is there, L naught, which is the, let's use capital L. So this is something that we are going to need. Yeah. So I think we have all that we need for the simplest possible, yet something that captures all the details so that we can use that differential equation that we have set up. So now we can write so what is going on here is a combination effect of the fluid velocity, the fluid moving, and the particles transporting, right? So let's first think about the fluid velocity. So the V fluid, can we express the V fluid in terms of the theta coordinate system? So what do you think should you write if you are trying to express V fluid in terms of the r theta coordinate system?
Yeah, this is the magnitude times the base vector.
True, but that's saying if you are these are the two components, V r and V, right? Can you enforce more conditions in there because we are trying to get something which is simplest possible. Yet captures most of the realistic information. Can we imagine that this is something? So if you think about a packet of air moving through the system, it is moving like this. I don't know if it would be clear enough, but this packet of air moves directly like this. So like this. So what that implies is V theta is always there, but can if I say something like this, can you say something about what the VR is? If it's going straight along the angle. Exactly. So that is a reasonable estimate, reasonable, I would say, assumption that VR is zero. The flux is moving directly like this. So we can write the V fluid as some scalar number V fluid times theta unit vector. Similarly, not similarly, but of course, like if you resolve the components of the other phase that we are talking about is the V particle. So V, so this is for the particle, this is for air. So V, now tell me what the resolution in these two components should be for the particle velocity. There will be V theta and V R, but can we say something about either V theta or V R? We cannot. We cannot. So it depends on the particle size whether it's going to follow the same lines or if they will follow the same lines. We need to chart out all the details. We need both the components for the particle velocity. So it should be V theta unit vector plus VR unit vector. Okay. So now let's. Are we stopping at noon right now?
Let's not follow. You can just complete these things.
Okay. It will take a while to complete this derivation, but let me go somewhere and then continue. So these are the two representations for the two velocities that we are trying to think about. Now let's come to the equation that we have just derived. Tau dV bar dt is V fluid minus V, right? From the previous equation. Let's now plug in what we just wrote here. So tau ddt of V theta unit vector plus VR unit vector is equal to V fluid bar is V fluid theta minus V theta unit vector minus plus VR unit vector. Do correct me again if I make a mistake. So this is it, and let's now break the left hand side apart. So tau dv theta dt times unit vector plus tau v theta d theta of the unit vector dt of the unit vector plus tau dvr dt times the unit vector r plus tau vr dt of the unit vector r. Right? I could have taken tau out, so let's take that. Okay, so now on this side, if I on the right hand side, if I club the theta and the r terms together, so V fluid minus V theta minus VR r. Okay, so the obvious direction where we are heading into is we will compare the theta and r components on the left hand side. That's the generic technique, and then they will still be differential equations which we have to solve using initial conditions. Fine. We have the terms for the theta and r components over here and over here. What is the derivative of the unit vector? What is dr dt and d theta hat dt in the cylindrical polar coordinates? Anyone remember this off the top of the head? Probably not. I did not either. So if you remember, do they have access to the cloud folder now? No. I don't want them to access them right now, but they have access.
I said, yes, this is right. This is.
Okay, so let me just quickly show you something here. So this is a screenshot that I took yesterday. Of course, I don't have internet either. But if you go to the lecture, yeah, I think you'd find them under journal papers. So if you go to the journal papers, there is a document that I have prepared called coordinates. So there are all the derivations for whatever the sub derivations which are not very, they are not very mechanics derivations, they are mathematical derivations for the coordinate system transformations, they are there. So if you have any doubts, you can go directly to that folder. Okay, let's carry on and write this one out. So you will see from that document in cylindrical polar coordinates, the time derivative of the unit vectors so see, I think it's called coordinates PDF on shared folder. So dr dt is theta hat or the theta unit vector d theta dt, and d theta dt is minus r hat theta dot. So now it becomes easy. We can plug in this into the previous formalism and then try to separate the theta terms and the r terms out. And that will help us form some revised version of the differential equations that we can solve, and then we'll see what happens after that. So let's stop over here because then, yes.
The first one is theta hat, theta dot or r.
Theta hat. Dr dt, dr dt. Yeah, it should be theta dot for both. It should be theta dot for both. But once you guys have internet access, you can quickly check if I typed it wrong. And in fact, when you guys have internet access, could you please take a screenshot of this page and bring it back in the next session? Okay, so let's stop for now.
Read that through again.
Yes.
Yes.
Carry it. Okay, so in the previous session, we had left off over here where we started out trying to apply this equation that we have been deriving since based on the material that we covered yesterday, and then we derived this particular form. So we are trying to apply this equation to track particles in an idealized respiratory domain now, unlike what we did yesterday when we were not assuming anything specific in terms of the anatomical realism of the geometry. So now we are trying to apply this to figure out the particle transport trajectory. And just as a recap, this is the geometry that we assumed probably is a good estimate of the upper respiratory tract. This is circular and then straightens out. Eventually, when we solve the numerical example, we'll see that we can adopt realistic cross-sectional areas, lengths in this geometry, and then figure out the answers for it. Cylindrical polar coordinates. This is what we figured out for the fluid velocity and the particle velocity. We are assuming that the packet of fluid is moving like this, so the radial component was assumed to be 0, so it's just v fluid theta unit vector, and then for the particle velocity, it does have both theta and r component. Now, coming back to that equation, we are just plugging in the result fluid velocity and the result particle velocity. And as we figured out that there would be some terms that are time derivative of the unit vectors. So these are the terms that I said are correct, and I think there was a confusion if they are correct or not. Just for folks to know where to access this, so I have uploaded this document under. So if you go to the cloud folder that was shared with you guys, there is a folder, subfolder called Journal Papers. There, look up this coordinates document. If you go to that document, so this has other details about different coordinate transformations. But I think if you go to the very last page, this is where I show dr dt and d theta dt. So dr dt is theta hat, theta dot, and d theta dt is minus r hat theta dot, which is what, if I go back now to the document, is what I had used. So the obvious next step would be to plug these things back into the previous equation. So let's do that, and then we are trying to isolate the theta component from the left hand side and the right hand side, and the r components as well, and see as we equate those components what we can get from there. So folks who just joined, we are trying to clarify whether these equations are correct, which we figured out is correct, and the corresponding document is under the Journal Papers folder on your cloud folder. Okay, so let's plug this into this equation, and again I am doing it here live, so if you find anything wrong, just let me know. Okay, so therefore putting the time derivatives of the unit vectors in the previous equation, we get, so the previous equation was this. So let me just copy the part. So tau dv theta dt times theta hat plus v theta d theta hat dt. So d theta hat dt is minus r hat theta dot plus dvr dt r hat plus vr dr dt is theta hat theta dot. And then on the right hand side, v fluid minus v theta theta hat minus vr r hat. Okay, now let's write it in dt format. So dv theta dt theta hat minus v theta d theta dt r hat plus dvr dt r hat plus vr d theta dt theta hat. Okay. And this is equal to v fluid minus v theta theta hat minus vr r hat. Therefore, now we are ready to equate the components. So equating the respective components. So let's first equate the theta component. So we have on the left hand side tau dv theta dt, and then the very last term, so vr d theta dt is equal to v fluid minus v theta. And then the radial component on the left hand side is tau dvr dt. So today our equation B was this equation that we are actually using. So let's call this equation as C, which is basically the same equation, but now we have them with the cylindrical polar components equated and as a result two separate equations. So let's see what we can do with these two equations now. But to solve these equations, we have to think about the initial conditions at this stage, which is what we started to discuss, or someone was asking if we need the initial conditions. But let's now actively think about what initial conditions could be reasonably assumed to solve the system. So initially, at t is equal to 0, so at t is equal to 0, what is going on? So in terms of what we are working with here is this basic system, right? The v fluid vector is the v fluid theta, and then we have v theta and vr for the particle velocity. So that being the case, let's brainstorm a little bit. So for the particle velocity, we have v theta as the theta component and vr as the radial component. Anyone guess what the v theta could be at t is equal to 0? Or what could be reasonably be assumed for v theta at t is equal to 0? Huh? Yeah, tell me v theta first and then you can think about vr. V fluid, someone I probably heard v fluid. Yes. So as you embed the particle, you can assume as a reasonable estimate that the particle is first moving with the fluid velocity. It doesn't have any r component as such. So we can assume that v theta is almost equal to v fluid initially. So that's an assumption. It probably is not precisely correct, but it's a reasonable mathematical assumption. The other thing that could help us is related to the geometry. So for example, if I look at this particular diagram, we can also write also the S, which is an evolving parameter over here, is R times theta. Do you guys agree? So S is R theta, but if we are rather tracking just the central part, we can also write this as S is equal to L naught theta, because that's how we are determining S, right? We are not determining S from any random point. So it is from the center of this inlet. So S is always going to be L naught theta. Okay. Now, if that is the case, if we do take time derivative of this equation, this second equation, S is equal to L naught theta, what happens then? So if we take ds dt, L naught is constant, so d theta dt. So d theta dt, we are going to find whatever value we get for d theta dt from here useful in those equations, fine. But what is ds dt? Can we assume something for it? ds is, can we say that ds dt is v fluid? That is how the fluid is moving, right? We are talking of this as a packet of fluid moving with the s being basically the centroidal section, centroidal point. So can we write something like this, that this is hence v fluid L naught d theta dt?
This we are saying that just at the instant.
Uh, at any instant, not at the instant, but here for that matter, we are talking about t is equal to 0.
Cat equal to the particle is at the center.
Right.
Then
So basically think about the particle following this particular geometry. We are placing the particle at the center, and what
Go into that those equations.
yeah, 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 yeah. So basically what we are getting from here, so this can be plugged back into any of these equations. So that's what I'm going to do next. Okay, so let's, what, as he suggests, we are actually going to supplant this d theta dt into the previous equation. So let's write that down. So d theta dt is v fluid over L naught. Let's now go back to the second equation over here. We could have used the first equation, and you can do that. What I'm trying to get at is show you a result that was derived rather recently in literature, and the fact that we can derive that based on the mathematics that we have been developing for the last 2 years. So let's use the radial component and see what we get from there. So we have from the second equation of the second sub equation of equation, we have tau dvr dt minus d theta dt is v fluid over L naught, that we have found out. But there is one v theta. So what is v theta here? We have assumed that at t is equal to 0, v theta should be the v fluid. So we put that here. So as a result, this becomes v fluid square, right? So we are putting both v theta and d theta theta from these two equations that we have derived. On the right hand side, we have minus vr. Okay. Let's now try to take the dvr dt on one side and put the rest on the other side. So we have dvr dt is minus vr plus V fluid square by L naught divided by tau. The next thing would be to integrate this. I'll take it slow because I'm bad at integration, so I'll do it by substitution, not to miss anything from here. So let's assume that this term, the numerator, I'm going to assume it to be something. So let's assume that this negative VR plus V fluid square over L naught is some term beta.
Tau is equal to VR by tau. Minus VR by tau plus.
Oh, right. VR over tau. Yeah, you're right. Yes. So let me just scratch this part for now. It would be too crowded. So what we should have is from this second sub equation dVr dt is negative VR over tau plus V fluid square over L naught. Right. Correct, right? Yeah.
Would you have assumed V theta at t is equal to 0?
V theta? Yeah.
V theta equal to V fluid at t is equal to 0.
Yeah.
But we are integrating it over the entire thing.
Yeah.
So how can we justify this assumption?
So V theta is a function of time, right? So it can change over time. But what we are assuming is that at t is equal to 0, that V theta value was V fluid. Now, in terms of, okay, now I get your question. Is your question something like, is the V theta going to stay constant throughout?
Yes, throughout the.
Right. So my argument is yes. So if you think about a particle moving, if it is following the exact streamlines, something with a very low Stokes number, for example, it's always going to have that V theta, which is the V fluid, which is staying constant in this case, and it is moving with the streamline. But if a particle has inertia, there would be a radial component, right? Like if it has a strong enough mass, it moves away from the streamlines. And that would be done with the VR, which is something that is additional to that V theta effect. And as a result, V velocity is different, of course. But that V theta part is dictated by the fluid motion. That's what the argument is.
V theta also I think can change.
V theta?
Yeah, when we talk about inertia.
It depends on what you mean as the change. So you are saying that if the particle is,
Because I think it can be so that.
yeah,
So I use that V theta also can.
If the tau is very big, so the Stokes number would be like very high.
yeah. If the Stokes number is very high, then V theta would change. But with the Stokes number being very high, the point is whether the particle would have enough time for the V theta to change before it goes on the wall because of the VR. Especially because we now have this circular tract, right? With the Stokes number being high, that means that the particle also has high inertia. So there is the other contouring effect, which was not there yesterday. We did not have that kind of inertia.
Maybe we can integrate this from tau to some time, because at t is equal to tau, the V theta regimes.
Yeah, yeah. That could be done as well. And this is an open topic in the sense that the paper that I'm trying to derive the result that we are trying to derive was just published a few months back. And the assumptions that are going into this work could be improved, right? And that itself leads to the possibility of new work that is publishable at a good enough journal right now. So let's move on from this. So this is correct. So let's call this equation D. And from here, yeah, this is what I was trying to get at. dVr dt is minus VR plus tau V fluid square by L naught over tau. Right? So now it is correct. So I have that balancing term over there. So let me replace this numerator with some single term. So minus VR plus tau V fluid square by tau is, sorry, by L0 is some term beta. So dVr dt is minus d beta dt. So therefore in D we have minus d beta dt is equal to beta over tau. Right?
Plus the
Yeah, so this dVr dt is, so I'm using this equation. dVr dt is d beta dt, negative, and then that entire numerator is beta divided by tau. Am I missing something?
on the right hand side, it should be just beta
Over here?
No, it is correct.
So basically I'm using this equation. Okay, so let's now change the sides and do some integration. So d beta over beta integral minus 1 over tau dt. So integrating this becomes natural log of beta minus t over tau plus some constant. So to evaluate this constant, let's think about what is happening at t is equal to 0. So at t is equal to 0, beta we have already assumed to be this numerator that we had replaced, right? So this numerator over here. So at t is equal to 0, it is minus Vr plus tau V fluid square over L naught. At t is equal to 0, we said that the particle does not have any radial component to its velocity. So this is 0 at t is equal to 0. So we are just left with tau V fluid square by L naught. So if we plug this back in over here, so at t is equal to 0, therefore ln of tau V fluid square by L naught is equal to, t is equal to 0, so the first term on the right hand side is 0 plus fluid square by L naught. So let's move this over here. So we have natural log of beta is minus t over tau. Actually, this last step is wrong. We can just use this constant to be the natural log of this entire term. So let's put this directly over here. So minus t over tau plus log of tau V fluid squared divided by L naught. Okay. So now let's get the logs on one side. So ln beta divided by this term tau V fluid square by L naught is minus t over tau. So beta divided by V tau V fluid squared by L naught is e to the power of minus t by tau. So let's go to the other page. Now let's put what we had about beta back over here. So beta is minus VR plus tau V fluid square divided by L naught is equal to tau V fluid square by L naught e to the power of minus t over tau. Or VR is 1 minus, so tau V fluid square by L naught 1 minus e to the power of minus t over tau. So this is the time function for VR, the radial component. Now going back to the geometry over here, what are we trying to study here? We are trying to study the whether we can form an analytical framework that can predict particle deposition. Those particles could be pathogenic aerosols, those particles could be pharmaceutical particulates. The theta component as such is useful but not as useful as the R component, in the sense that if a particle is over here based on the same theta, had it been over here, it is going to get deposited, right? And the main distinction between this point and this point is controlled by what is the R. So if you make sure that the R component is big enough, it will be landing on the walls even if theta is small. So the theta value, the range of theta value would not necessarily tell us anything. Because for the same theta value it can be deposited, it might not be deposited. But the R is a certain criterion that can tell us whether the particle has deposited or not. And that is the reason why we are trying to drive this analysis towards the R component. And now, with that logic, we do have how VR is varying over time. So now we are very close to a solution which can develop a generic criterion for wall deposition. We just have to do one more layer of integration. So we have the VR. So therefore, to predict the wall deposition criterion, we have to integrate again. So dr dt is this right hand side on equation E. So tau V fluid squared over L naught 1 minus E minus T over tau. Right? So let's now do some more integrals. So we have, let's assume that minus T over tau is U. Therefore dt is minus tau du. So we are going to use this one. So therefore integral of E minus T over tau dt is minus tau e to the power of u du, or minus tau e to the power of u, with u being minus t over tau. So let's use this directly over here. So we have dr tau v fluid square over L naught integral dt minus integral e to the power of minus t over tau dt. And this becomes r as a function of t, tau v fluid square over L naught t, and then this term, so plus tau e to the power of minus t over tau, right, plus some constant c. Let me know if you see something that's wrong. Okay, now again we need to evaluate this constant of integration. So the initial condition over here is at t is equal to 0, we have to figure out some initial condition that can be used here. So like before we were trying to find the initial conditions that relate to the velocities. Now we have to think about the initial conditions that relate to the spatial position. So what is the initial position or what is r at t is equal to 0? Second? Yes, so we had assumed the distance from the center to be L naught. So at t is equal to 0, it is L naught, correct. So at t is equal to 0, we have R as L naught. That being the case, let's put things back here in the equation that we just derived. So L naught is equal to, this term is 0 because t is equal to 0, this term is 1. So we basically have tau square v fluid square divided by L naught plus C, and hence C is L naught minus tau square v fluid square by L naught. Right? Okay, let's now put this back in this equation and try to simplify this a little bit. So therefore RT is tau v fluid square over L naught t plus tau e to the power of minus t over tau plus this C, which is L naught minus tau square v fluid square by L naught. Okay, so this is interesting because where we are heading at is, if you think about the geometry that we started out from, L naught is the central location, and then this particle is deviating from that central streamline, right? And that extra term that we are getting, so there is this L naught here, but the remaining terms can be plugged together, of course. And those remaining terms can help us determine whether the particle is going to this upper wall or lower wall. So it is very interesting how it can be done. So let's do that. Let's simplify this a little bit, keep the L naught one intact. So we have RT is L naught. Let's take this tau v fluid square common. So tau v fluid square over L naught t plus this tau is common, so tau times e to the power of minus t over tau and minus 1 for this one. Let's call this equation F, I believe. So now the rest of the analysis could be driven within this term, which signifies the deviation from the central streamline. Okay, so let me write down what the couple of things that I just said into words before we use that particular term. So for example, as this RT becomes L0 plus L. So what is capital L? It's the radius that we had assumed. So if it exceeds that value, then that means that there is upper wall deposition. So the particle will deposit on the upper wall of the idealized respiratory geometry, right? But that is not all. It can also deposit on the lower wall. So L naught minus L is also a valid criterion. So let me write that down as well. So similarly, for lower wall deposition, this RT would be less than L0 minus L. You can think of this as greater than equal to and less than equal to as well. That's just some triviality. It doesn't matter whether you say equal sign or not. Basically, you are crossing that threshold, either the upper threshold or the lower threshold. So let's use this and try to set up the criterion. So therefore, for upper wall deposition, so we are using this E form. So L naught plus tau V fluid square divided by L naught T plus tau e to the power of minus t over tau minus 1 is greater than L naught plus L. So the condition comes out as tau V fluid square over L naught T plus tau e to the power of minus t over tau minus 1 is greater than L. So here L is the mean radius of the respiratory tract. But so L is the mean radius of the respiratory tract. So this equation, does it look familiar to any of you? We just read this equation from the last time. So I was working on this lecture material in December during the Christmas break. My wife and daughter, they were traveling to my in-laws place, so that gave me a lot of downtime to work. So I derived this equation, and I could have gone in a different direction as well. I could have used the other components, but I first thought that the radial component is interesting, so let me derive this. So I derived this equation. It sounded kind of nice, like the way the derivation was done is kind of elegant. And then I knew of a paper which I have been dying to read for a while, because especially because it's coming from a collaborator, Sunny Ben, who is on some of my clients. So I started to read the literature, and then I saw that he has already read this. And he published this just a few months back, 6, 7 months back. So that's why I made you guys at least take a look at that paper. So I'm going to put the paper on the screen now. So this was the paper, simplified models of aerosol collision and deposition for disease transmission. Since all of you did read the paper, anyone wants to just summarize in 3 4 lines what it was about? Not the details of the scientific equations and whatnot, but what he did. Anyone?
In this basically two models are described. One is the aerosol deposition, and another is if there is a difference in how a particular deposition happens with respect to the aerosol specific disease.
Yeah. Okay. looked at two different time scales first of all and time scales. So first, how is the room level mixing happening? So that is what the paper starts out with. And then he goes to what is happening, what is going to happen inside the respiratory tract.
Per hour, how much is the circulation is happening?
Yeah.
What is the radius of the infected person?
Yeah, so that's the root level modeling. Like what kind of transmission an infected host might be carrying out with the others. And then once, let's imagine that I am infected, so I am giving out pathogens, and now Dr. Shamandu is getting infected, is getting exposed, and he is inhaling all these pathogens, and what is the generic trend of the particle transport inside the air? So that's where he went into next. But because I knew the overall story, that this is what he was trying to do, and what I don't believe that he claimed that he did all this work because he had like 2 layover days at a conference, so he had nothing else to do. So apparently he did all the calculations and that. I don't believe that. But anyways, but this was a very elegant piece of work. I have been meaning to read that. But since I was developing material for this lecture, I thought that okay, the story is gradually getting what Sun is thinking that over. So after I stopped my calculation over there, I started to read this paper. I think I noted down the equation here. So this is equation 13. So I'm going to skip the details of the paper, of course, and I would encourage that you guys eventually go through the details because things like this could be done without any kind of hardcore computational support, without any experiments. You just need to plan 2 empty days around a conference and you can get this paper done. But let's go to this equation over here. So this was the room level modeling that he did. And then he's going to the aerosol deposition inside the respiratory tract. And eventually he's coming up with this particular equation over here, equation 13. So equation 13, let me make this small. I don't know if it is visible or not, but let's try with this. So we have, I think I already missed equation 13 here. So yes, this equation. So what he had was alpha u in L over L naught. Now the word alpha threw me off because the symbol alpha threw me off because we only use alpha for time. So if you read the paper, you go back a couple of pages, alpha was done. Alpha was the particular section element in this case. T plus alpha is tau, e to the power of minus t over tau, minus 1. So here it is, based on the very basic level mathematics that we started out. Assumptions that went into this derivation. And you can expand on those assumptions, maybe make it more nuanced, and that itself could be a new independent set. But let's try to use this and see what it tells us about particle transport trends in the respiratory area. And for that, we have to do some numerical solutions. By the way, how many of you does have access to MATLAB in this room? Maybe through your laptop? Anyone? Not anyone? Okay. So then I have saved the codes on the share folder. I'll try to run them live over here in front of you. So feel free to use them later on. Okay, so just as a note, so compare this to equation 13 of GIAN Scientific Reports 2023. Okay, now for the what we are trying to do next is use this equation to figure out what the generic trend of the particles could be in terms of the spatial trajectories based on two very widely defined sizes. So I think in the work here, I'm going to show two particles, one with diameter zero point 0.1 micron, one with diameter 100 micron, and see what happens. And check this particular criterion for that. So so based on the particle sizes, let's first figure out the particle relaxation time, that cofactor that is outside the bracket, and then we can take a look at the MATLAB code that I wrote.
So from here we can conclude that if the time is greater than the particle relaxation time, then the particle will definitely deposit on this upper wall of the.
And actually, like once I run the code, you will see that the time it would take for the particle. So basically, the time it will take for the particle to reach the wall is widely different for the smaller particle with respect to the bigger particle, and which is expected. Based on the length of the longer time scale, it will be quite obvious where it is going to land. And based on the length of the shorter time scale, it will be also quite obvious where it's going to land.
So in this like wave fluid is the ambient fluid for the particle, right?
Can you repeat the
So
question?
like wave fluid is the fluid velocity.
Yes.
And the particle is not there.
Yes.
So does that mean that the particle hasn't disturbed the flow?
It is so. We are not, this is not a coupled system. The particle is not disturbing the flow. The flow is, so think about the way the equations have been derived since yesterday. The drag force is coming from the flow field. The flow is impacting the particles, but the particles are not. And that assumption will be true even for the safety simulations that hopefully we are going to run tomorrow, day after tomorrow. So it's a decoupled system in that sense. Now, your question could be, is that a good assumption? Because it is not necessary that there is going to be a momentum exchange between the particles and the fluid. So while you can develop it as a two-phase system in your numerics, but the eventual benefits out of that is so slim that it doesn't make sense to make it that complicated. But that is a foolish argument in certain sense. So I do plan to go into that territory and run it as a two-phase system. But then again, two-phase, like for example, I have other projects where we do have to consider the multiple phases. Like if you think about movement in very thin tumor vessels in blood channels, there the RBCs are big enough because RBC is what? Around 8 micron, white blood cells are around 16 micron, and those channels could be around 30-40 micron wide. So there you have to think about RBCs and WBCs as different phases. But over here we are talking about, you saw the dimensions, right? So even when you go to the alveolar channels, you have 500 micron. And the particles that we are talking about are 10-20 microns. So do we really need the multiphase assumption? Probably not. So, but the other thing is, not many fluid mechanicians like us have been active in this field. So if you go to a medical school, you might not be sure about what all those work might entail either. So maybe because we are in this field and these things are evolving, we should try out all our tools. Okay, so as I said, we are going to use two diameter examples and 100 micron. This is the formulation that we are dealing with. So tau is there, and tau does have the slip correction factor based on the particle size. Now one may argue that the slip correction factor based on the particle size. Now one may argue that do we need the slip correction? We don't need the slip correction probably for the 100 micron size. We do need it for the 1 micron. And that I think Devananda is the reason why the small particles have higher drag. So we can discuss this later on, but it is because of drag. So we can discuss this later on. It is because of the slip factor. But anyway, so we do need the CC correction. So let's put it there. So CC is 1 plus 2.5. So CC is 1 plus 2.52 lambda mean free path divided by D. So this is 1 plus 2.52 0.067 by zero 0.1 in the first particle and 1 plus 2.52.067 by 100 in the second particle. Can you give me these two numbers? And let's stop here because after this I'm going to run that code and try to explain the code, so that will take a while. So let's calculate this series and then we can pick up the rest of it on. How about the first one? 1.001. Let's take 1. So this is D is equal to 100 micrometer. So that's why I said that you need it for the small particle, maybe not for the bigger one. So we are going to use this CC to calculate
Can you become in this system?
different parameters that appear on left hand side of this inequality. So V fluid is given to us. The rho P, we are assuming water dust aerosols or droplets. The slip correction factor is 2.7 for the smaller particle, 1 for the larger one. And we need the C in the particle relaxation time. So let's evaluate that now. So tau is rho P d squared cc over 18 mu. So this is equal to 1000 is the density times zero point 0.1 is the first particle size micron, 2.7 is its slip correction factor divided by 18, and 1.8 10 to the power of minus 5 kg per meter second is the value that we have been using for mu air is the viscosity coefficient. And this is for zero point 0.1 micron, and then we have 1000 times 100 10 to the power of minus 6 square. The correction factor is 1 now and 1.8 times 10 to the power of minus 5. Can you give me these two numbers? 8.3 into 10 to the power of minus 8.3 into 10 to the power of minus 8. So, yes. So I have 8 times 10 to the power of minus 8. Let's just use that. What's the second one? 0.0308, yeah. So I have 0.031. Okay, so what else do we need? So again, we are trying to use this criterion G We have evaluated the tau, we know V fluid, we don't know what is L naught, we don't know what is L. So let's think on those. So what is L naught? So if you think about the geometry over here, L naught is basically the radius of curvature of the track, right? Now, based on the area that you are trying to apply this technique to, you can figure out the main radius of curvature. That's up to you. Typically, what I've assumed is coming from some very rough estimates. So the value that I'm going to use here is L naught to be 5 centimeters, which looks like a fairly reasonable estimate here, because if this is being approximated as a circle, that being the radius as 5 centimeters, it seems reasonable to me. But precisely, you can probably take something which is closer to whatever the actual value is. And this by itself would be another new line of research. You can get a new anatomic geometry, which we have a lot of in our lab. You can develop the surface the surface curves that delineate this space, and then you can figure out what is the mean radius of curvature and apply that. And I'm sure no one has done anything like that before. Even in the paper that I showed you, he did not get into the anatomically realistic geometries. For now, let's assume that L naught is 5 centimeters. So 0.005 meter, and L is the radius, right? I have used 0.05, but the thing is, let's quickly take a look at what a possible radius could be for the construction. So we are trying to send drugs to some granulomas, some tumors that are formed in this region. So this is a cross section at the lens. On the other hand, if you think about the other geometry that I was sharing with you guys, so this is what the slit cross section is. Now, if you ignore the thin regions at the top, if you just focus on the thicker parts, what the corresponding radius would be, that is up to you. You can measure it and you can make it as accurate as possible. Maybe think of it as the hydraulic diameter of hydraulic radius of this region, figure out how much is the dominantly weighted region, and then figure out the radius from there. For this particular problem in class, I'm going to use some approximate values. But again, I'm going to reiterate that these are research questions, and you can use the precise values, and that itself can lead to a new line of work. Okay, so the value that I have used is 5 centi, 0.5 centimeters. Yeah. So yeah, this one was wrong, right? This is 0.05. So L naught is 0.05, one or smaller. I have used 0.005 meters as the radius. So let's see what we get with this values that are probably close to what is reality, but still are not very accurate. Now, before we go into MATLAB, let's quickly figure out this factor that we saw appearing in equation G. So this factor tau v fluid square over L naught. So how much is that? So tau v fluid square over L naught is, you have the taus and the v fluids over here. Can you give me the corresponding numbers for d is equal to 0.1 micron and d is equal to 100 micron? So for t is equal to 0.1 micron, 4 into 10 to the power of minus 5. Yes. What's the second one?
15.5.
15.5. Yes. So now we have all the values that we are going to need. So let me write down the problem statement. So thus the formalism in G, which is that equation, that inequation, the inequality that we have derived, in G could be simplistically written as the cofactor. I'm just going to, in the code, you will see that I'm just using the alphabet A. T plus, I think I'm using B for this, e to the power of minus t over tau. Tau is B minus 1 minus L is 0. So basically, A is that tau df square over that factor, and B is tau A. And I brought L to this side. So what I'm going to do is find the numerical solutions that would put the particle at the wall. And what would be, so if I solve for this, A has a numerical value now, B has a numerical value, L has a numerical value. So the only unknown in this equation is this small t, the time. So I'm going to figure out what is the time t for the particle. In the first case, the particle 0.1 micron, and in the second case, the 100 micron particle. How long does it take for the particle to reach the wall? Does the argument make sense? So from inequality, we have now moved to an equality condition. Okay. So where t is to be solved, to figure out the approximate delta t until the particle, or for the particle to deposit on the upper airway wall. We need to be cognizant of the fact that we are still talking about the upper wall as such, because that's what the function was. To pick up the position of the lower wall, we probably have to change. We have to change that equation. If we have time, we can take a look at that as well. So that's not what was done. It's just looking at the upper wall. Okay, so we are going to do this derivation. So this is now the problem statement. Do this derivation for d is equal to 0.1 and 100 micron. For the numerical solution, you may use the provided MATLAB code. So one thing that I'm trying to be curious about, and something that I haven't done yet, is what if we do pick the lower wall deposition. What changes in that criteria? Can you guys look back at your equation and tell me what is the precise thing that will change if instead of the upper wall deposition, we rather try to crack the foundation for a lower wall deposition? So this is where I was discussing this, right? So we got this G, and the conditions for upper versus lower wall depositions are up there. So our T greater than L naught plus L is upper deposition, and L naught minus L is lower deposition. So as a result, when we are using this criteria, and from this inequality, when we move to the inequality, we took L to the other side and it became a minus L. That minus L would be plus L. We rather try the lower wall deposition. So I haven't tested the code for that yet. I don't know if it would work, but we can try it out. But the thing that I think should work is the upper deposition. So let's try that. The reason why I'm unsure whether the other one would work is because we have to set up some initial trial values in the code, and that dictates whether it manages to solve for it or not. Okay, so let's now go to MATLAB. So by the way, again, if you go to our cloud folder, the MATLAB codes are under the folder called MATLAB codes. So you can use them directly from there. Do I need to make the font bigger or is this fine? Okay, so this is for, let's first do the point, the smaller particle. So we have already derived the values for the different parametric values for that. So we have the A, which is the TVF square over L naught, to be 4 times 10 to the power of minus 5, right? So 4 times 10 to the power of minus 5. And the B, which is the tau, the relaxation time, is 8 times 10 to the power of minus 8. Sorry, I am not really used to the keyboard of this computer. 8 times 10 to the power of minus 8. And L is SEM, which is 0.005 meters. And here I am trying to figure out the solution, but we do need to give an initial guess for the T. So let's see if this is the correct guess that would work for this particular example. So we know that this is a smaller particle, right? So it stays airborne longer. So the initial time estimate that I started out with is 100. If we do change this initial guess, let's make it smaller. What happens then? Let's make it 1. The solution doesn't converge, which is understandable because the solution cannot be anywhere close to that small value for the initial guess. On the other hand, if we do change it slightly higher, so let's make it 50, does it work then? It doesn't still. Let's make it 80. Now we again converge to that same value that we had before, 125. Now this is for the upper wall deposition. Now what do you think needs to be changed here for the lower wall deposition?
As in minus plus.
The minus and plus on line 11. So this becomes plus. Let's see what happens if I run it. So we don't converge with this one. Let's start from smaller. Let's try 1 first for the initial guess. Still nothing. So let's go to 10. Still nothing. Let's go to 50. Doesn't work. Let's go much bigger. 500. Nothing yet. Yeah, so I would leave this as an assignment for me and for you guys to see what happens if we do change that sign for L. And there is probably a reason why Sunny did not dare to get into that territory, and which we are missing maybe right now, but physically there is no reason why we cannot get that either. The only thing that I can think of is the typical trajectory of the particle, since we are not counting in gravity, it's physically almost impossible for the particle to fall back down, moving through the straight lines. And that could be a reason probably there is no real solution for this particular condition. With that. So, that's a good question. Could there be a physical solution if it is indeed that?
I think it is a positive quantity over.
Right, right. So if
it is not
this can never be equal to 0 because and that's quite elegant in the sense that that particle can never go down, as if there is no solution possible for this particle. We might have had something if we had counted in the gravity term, but here we are not doing that. So thanks for finding that out, but yes, this is physically impossible. So we won't have the lower body position. So make a note of that where we did mention the lower body position. So let's change it back to minus L, but let me also make a comment over here. So this is where we derived equation G. So this would imply that tau Vf square over L naught plus T plus tau e to the power of minus T over tau minus 1 plus L will have a real solution for T, which cannot be true. So in this approach, we are not going to get the lower boundary position because both the terms are above this. Could this term become negative? So this term over here, this is e to the power of minus t over tau. So, no, it can never be negative. So the lower wall deposition is not possible over here. Okay, let's move back to the code again. So I think I have corrected this. Let's run this again just to be sure. So 125. So now let's try out this was the smaller particle. Let's try out the bigger particle, for which we have the parameters as A, which is tau, as 0.031, and sorry, A is not tau, A is tau Vf square over L naught. So that is, how much should A be for this one? You can look at your notes. 15.5. Tell me how much B should be for this one, which is tau 0.031, and the L is still same. Now, this one, if I keep this same initial guess, let's see what happens then. We don't have a converged solution because this is a much bigger particle. It's not going to take that long of a delta t before hitting that condition over there. So let's make this smaller. Let's make it the initial guess to be 1. And we still don't get a converged solution, so we have to make it much smaller. Let's try the next smaller magnitude, the order, so 0.1. Still nothing. So let's make it one order smaller, 0.01. And now we have an answer, 0.0046 seconds. So that means this particle, the moment it is led into the S, it deposits within a fraction, within a very small fraction of a second. That means it is going to deposit in the upper airway. Yeah. So I don't think Sunny tracked this time interval down in its work in the paper. So feel free to get in touch with me if any of you here have interest in following up on this problem. Because physics is just lying over there. And of course, I just had 2 particles of this, right? So you can develop a parametric, a phase portrait by trying out this code and figuring out the T critical needed for each such size. And then a nice study would be comparing this theoretical estimate with the corresponding safety generated estimate for a similar amount of geometry. So if this interests you, let me know, and this could be a collaborative project between us. Any questions?
And it is just like, it's just starting time of 1 second after this because of time to create the
Yes. So it takes points. So starting from the central point of the inlet cross section, it is supposed to take 0.0046 seconds to hit the wall. Given that is the flux that it is going to move through, 5 meters per second. And the numbers are quick estimates, right? So we can make this biologically, physiologically more realistic. But this gives us the order of magnitude. Any questions? Okay, so let me note down some comments over here under each of these codes. Okay, so this is the one for t is equal to 0.1 micron. So this, the delta t being more than 2 minutes, implies that therefore there is barely any chance for upper airway deposition. And for zero point 0.1 micron, realistically, even while running CLB simulations, we don't see much upper airway deposition. So, although I have kept the word barely, but it could be as good as there is no chance of upper airway deposition. On the other hand, if we had picked out something like say 1 micron or 5 micron. I won't go into that because we have to then again do the numbers for the tau and the cofactors. Then this what barely makes sense because some of them might still land in the upper area. Now, in the second case, when we have and this to your point, like the size threshold analysis, we can do it this way as well. In the second case, when we had the D to be 100 micron,
Just one thing.
yes.
Just because we have used this branch from because it's just sitting there, and then when branching also takes place, there is a chance that it can hit the center.
Yeah, so what he's assuming is basically if you think about the geometry here, he's talking about, well, he's not talking about that, but what I perceive is he was trying to do is one side of there. Topologically, that would be a very different problem. You have to understand.
But if such kind of model can be made for a single branch, then it can be easily sort of scaled down to
Within the pattern.
all the branches.
Yeah. But it would be challenging in I don't know the details yet because we have not done the work, but one thing that we do know, I need a chalk. I should not be moving this one. So let's keep it here. So it goes like this. What happens then?
We have simplified 2D version because he has simplified it so much.
Yeah. Now I'm trying to figure out where you might encounter this.
And this can be axisymmetric also. You can sort of make it axisymmetric and just do one side.
So basically, you suggest this region.
And this can be scaled down at every level because of sort of if we are assuming everything that then this can be a good assumption.
Now, one thing that people have definitely seen for a system like this, it is a very relevant system where if you look at the two sides of the nose, so think of this as the internal dividing wall on the two sides of the nose. This is called the septum. And then the two sides, I'm looking at my airway from the top down. The two sides converge together and then it goes further in. So the air comes in like this, but think about when acceleration occurs, that's exactly the situation that you were trying to describe.
Okay.
When the air is coming out. See, the thing is, when you describe it as an overtly simplified analytical model, I don't think I would agree with you on that. The reason being, we are going to see this way that in terms of the details of the flow physics, the complex flow structures like the vortices, they are dominant mostly after the variance in the tracheal region. The flow in the upper respiratory air space is fairly consistent in the sense that you can think of it as a pipe flow, which is basically what they're trying to do. If you think about this geometry that we used, the idea is not it's a pipe flow, right? But like in this code, we try to use the numbers extract from the analytical geometry in terms of what is there, what is the radius of the cross section, etc. So it is more than a simple analytical model that is using out all the details. It's not like that. But we cannot do this kind of modeling for the entire area, which you are in the right track that if we do encounter this kind of transport, you have to think about a different model. Maybe there is one, but and it cannot be something like this. Yeah. Question? Any other questions? Okay. So over here, let me write my only comment. So this is 0.0046 seconds. So this is 100 micrometer diameter would undergo prompt anterior deposition way out, right? Because you cannot really include all the details of the geometric topology into the problem. At best, what you can do is something like this. When you have a block body, and what I was trying to get at over here was this T junction. So the T junction is an extreme version of this Y junction, and this again goes to further Y junctions as we go further downwind in the runs. Now, what people have seen is in flows like this, there are vortex tubes. Streamlines, this vortices should not be there, but they are there. And question is whether these vortices are relevant for the Y sections over here. So there is more going on. There is some more going on in my group as well, where we're trying to focus on this kind of T junctions and correlate our understanding, make it sort of like a
I
canonical
think
model.
this was something like Howard's group was doing.
Yeah, Howard has done this, and I think Gareth McAnally has done something as well, and they have collaborated together. And I think 4 years back at one of the DLT meetings, Howard posed this as an open question in the sense that they have just looked at this one. Uh, Frankly, there is no explanation why the vortex should be there because the streamlines they should drive this further, right? But no one else has really done this experimentally. What I have done is there is an archive preprint which you can find from my website where we did show that computationally it is there, those vortex fields are there. And the question is what particles get trapped over here? Is the particle that you're trying to track. Then those get trapped in this kind of vortex fields. And Gareth McAnally, he has also done some simulations on this. Okay, so any other questions?
No,
Mm, no, it could be turbulent. But there is a certain range over which and some of them they do look like T junctions or Y junctions. And some of them they do look like T junctions or Y junctions. Okay, so let's move on. So until now, what we have been doing since yesterday was just the particle. Until now, what we have been doing since yesterday was just the particle transport, right? So we developed equations for a single particle moving through the respiratory tract versus the thinner bronchial channels. Different terms could be relevant on the Navier-Stokes equation. So, to answer questions, on the fate of inhaled particulates, that is aerosols with d less than 5 micron, or droplets with d greater than equal to 5 micron, it is necessary to understand the fluid motion inside the respiratory tract. Now, while trying to understand the fluid motion inside the respiratory tract, the approach that we took with the analytical formalism for the particle transport might not be a very valid approach, where we idealize the geometry and then we try to get a generic trend on the particle evolution regions. Here we are talking about the flow field moving through this complex geometry. So the moment we start to simplify this geometry, we are going to lose those flow fields, right? So to give you an example, oops. To give you an example, when you have, let's assume you have a very complex geometry like this. So let's assume that this is the inlet and this is the outlet. So going by the kind of simplification that we have been using until now, that we try to sort of keep the topological nature of the geometry intact, and we assume that there is a geometry that is an equivalent geometry that goes like this, and maybe even diverge out a little bit to get the bigger cross section. And the claim was this two are equivalent. That's essentially what we have been trying to do until now. But now think about the flow field over here. The streamlines that go in through here might be creating some kind of recirculating flow that can lead to some vortex regions over here and maybe over here. But this is a simplified flow. Do you expect that similar flow field features would be there? You know, there is a smooth surface or smooth wall. So that approach of simplifying the geometry and then applying our theoretical ribbons won't hold the ground anymore. So let's keep that in mind. And we should be thankful for that, because then we won't know anything about what is going on across different subjects. Because, as I think I was pointing out yesterday, that all our anatomical geometries are different. In fact, the left side of my notes is different to the right side of my notes. So to figure out these differences, or to make or to develop some work that can directly impact a particular person or a group of individuals, we should be thankful that the flow field does react to the geometry. It's a geometry coupled system. So we should keep that in mind before trying to develop any kind of reduced order framework for this. Okay. So the flow physics within the respiratory airspace is a function of the anatomical geometry and the details and the geometric details can and do impact or do vary from person to person. Having said that, we will see, I think, tomorrow or day after tomorrow, that laryngeal constriction, the constriction that happens right before the larynx, is sort of similar across subjects. So how much how much it converges and then diverges is similar. So that vortex formation, the strong vortex formation, is fairly consistent across all subjects. The precise strength of the vortex might change a little bit. The location might change very little bit, but it is there. That is the general shape of the anatomy, which is true for any subject. Okay, so Keeping this caveat in mind, we can still try to derive some general description of the flow of the fluid dynamics. How do you think we can achieve that? We cannot idealize the geometry as we saw from there. What we can still do is use Navier-Stokes, try to non-dimensionalize it, figure out what could be the dominant terms, and that can help us develop a broad understanding of what might be happening in the upper respiratory areas versus in the high generation vascular channels. So that's where the approach is going. But before we go in that direction, the fundamental approximation or assumption that goes into the flow field is the fluid domain incompressible? And frankly, I never really thought about this question. I just assumed that it is incompressible. Is it okay to just assume it is incompressible for this kind of airflow? The Mach number dependence is less than 0.3. What are the different conditions for that? One is the temperature gradient difference. And that is the only thing that did not seem obvious to me because we are breathing in air. Forget about Ropar. If you come to where I am coming from right now, it is minus 32 degrees Celsius. That's what my wife told me right now. So they have delayed school start by 2 hours in the morning today. So minus 32 degrees Celsius, you are breathing in that air. Our tissues are at a certain temperature inside the body. That was one thing that I was concerned about, whether the temperature difference can sort of play against our incompressibility assumption. But thankfully it does not. So that is one thing. The other factors are, so for example, the flow rate, it does not exceed to that kind of level, of course. And in terms of the density, it seems like some folks from the medical community they tried to argue that maybe that is not reasonable to assume that it is incompressible, but then the air that we are breathing is mostly what? Three-fourths of it is what is air breathing? Yeah, three-fourths. So basically the components that get exchanged through the gaseous respiratory exchange process in the alveolar sacs, it's just a very tiny component of it. It does not really change the density much. We can assume, we can definitely assume that the air has constant density going in, but I'm not talking about what is going on in the exchange between the pulmonary channels and the alveolar channels. And still, because the component that gets exchanged is such a tiny fraction of the air, the density doesn't really change much. But these are not, these two, at least the density part and the delta T, the delta time, the delta temperature, they are not really obvious. And
So what really happens? Like we are let's say we are getting the air at minus 32,
yeah,
and as soon as it enters through the nasal pathways, it achieves kind of 37 degrees Celsius around.
the thing is, I have written a couple of papers on this. So basically, people or animals who live in cold climates, their nasal passage is much more tortuous. So it's like this. So as a result, the air gets warmed up very early. As human beings, our nasal passage is still tortuous as we know, but not as tortuous as say some of the mammals that live in this very cold regions. So as a result, we are not supposed to breathe in air outside that kind of thing. But it's a we actually in 2020 we had got a grant from the NSF just on this application that this tortuous nasal passage could it serve as sort of like a bioinspiration to warm up fluids or to screen particles that are embedded in the fluid. And we actually developed a mask filter design using bioinspired respiratory tract geometries for the filter channels. Okay, so is the fluid domain incompressible? Yes, it is incompressible, but let me write down the points over here. So a pure fluid flow can be considered incompressible if the Mach number is less than zero point 0.3. Now, that is true if the delta T is less than 30 Kelvin and the V flow is less than 100 meters per second, both of which are reasonably true in our case. Now, the other effect is about the density. So, how good is the constant density assumption? So, as Dr. Shamanto pointed out, nitrogen is the primary dominant component in inhaled air, around three-fourths. So, nitrogen comprises more than three-fourths of the inhaled air. Three-fourths of the inhaled air density, and is not exchanged across the airway tissues and lung epithelium. So if that is the case, the compounds that, as I said, that are exchanged, they don't really change the density much. So the variations in the other inhaled gaseous components like O2 and CO2 do not significantly alter the density of inhaled air. But this approach by itself, if you think about some ulterior applications where uh, think about the World War II gas chambers. These assumptions might not be true then, because the air that was going to be inhaled probably had some very different constitution, the compound fractions, and the way the gaseous exchange happens at the final generations of the quantum branching would have been messed up. So something to think about, and it could lead to other academic research as well. Okay, so with this being true, incompressible, thankfully now we can use the Navier-Stokes equation that we all love in its incompressible format, which oftentimes, if I ask my students, my American students especially, after all the fluid mechanics, they can never write Navier-Stokes equation. And I tell them that once my advisor threw out, and this is a true story. So I come from a fluid mechanics group, of course. My advisor threw out a graduate student because he could not write Navier Stokes after 3 years. So that was the reason why that person was thrown out. So if not if I am the chair of the committee, but if I am the committee member, my PhD students committee whose research is supposed to be in fluid mechanics, that's the first question I ask. right? The navier strips. If the person cannot, which they cannot sometimes, I tell them the story that you would have been thrown out of my research group, the group I am from. Anyways, I think let's wrap it up today. Tomorrow we are going to use the non-dimensional decomposition navier strip situation to say a few things. Before going into some more application-oriented problems, Dr. Shamunta is going to teach today and tomorrow.
Tomorrow there will be a change, like the topic is a solution.